In this segment, we're going to talk about specific heats. And specific heat is a property that we can use to calculate changes in internal energy and enthalpy for substances that exist in a single phase. So let's talk about specific heat, the definition of specific heat first. This is the energy required to raise a unit of mass 1 degree, and we can express that degree change or that change in temperature in degrees Celsius or Kelvin. It doesn't really matter since we're talking about a delta T, so it'd be the same numerical value, either whichever unit you decided to use. And it's a property. It's dependent on temperature, and it's also dependent on how you measure it. So let's talk about the two ways we can measure it. Number one, we can take our substance, we could put it in a rigid tank, and so we keep it at a constant volume, and then we add a certain amount of energy, enough energy to raise the temperature 1 degree. And if we measure it this way, we call it the specific heat at constant volume, CV. CV is defined as the partial derivative of U, internal energy, with respect to temperature. And you can see it written in terms of kilojoules per kilogram K. That's what your book uses. But you may see it written as kilojoules per kilogram degrees Celsius. And just keep in mind that if you have a CV and it's 2 kilojoules per kilogram K, that's equivalent to 2 kilojoules per kilogram degrees Celsius, because that temperature unit is referring to the temperature change, which is the same in degrees Celsius as it is Kelvin. So just keep that in mind. There's no unit conversion necessary. All right, the other way that we can measure it is by keeping the substance at constant pressure. So maybe you put it in a piston cylinder, 1 kilogram of your substance in a piston cylinder, you add a certain amount of heat, or a certain amount of energy, enough energy to raise the temperature 1 degree. And if you measure it like this, it's called the specific heat at constant pressure, CP. And CP is defined as the partial derivative of enthalpy with respect to temperature, same units as CV. All right, so there's our definitions. They look kind of ugly now, but they'll pretty up shortly. And we're going to use these relationships to calculate changes in enthalpy and internal energy for substances that are in a single phase, specifically for incompressible substances like a compressed liquid. These also apply for solids as well, because those are incompressible substances as well, and ideal gases. They're valid for any substance undergoing any process as long as you have one of those two conditions. It's either an incompressible substance and it stays in that incompressible substance, or stays in the compressed liquid, for example, stays in that region, or you have an ideal gas and for the entire process it's an ideal gas. So it's valid for any substance undergoing any process in those two regions, and it's not just for constant pressure or constant volume processes. The only thing that CP and CV have to do with constant pressure and constant volume are how they were experimentally determined in the first place. So just keep that in mind. Don't think that it's limited to only constant pressure processes and constant volume processes. All right, so this gives us a way, these CP and CV relationships give us a way to calculate delta U's and delta H's for a substance in the single phase without using those thermodynamic tables. But of course, we could use the thermodynamic tables. We've got a couple of options for calculating delta U's and delta H's. So let's talk about what those are. Number one, well, we could use those thermodynamic tables. So we've been using the ones for water. We can use those, but we actually also have some for air. So this is A22. You've got English units with A22E. This assumes air behaves as an ideal gas. And one thing that you'll notice is that the only thing you need to know to read off an H value or a U value is the temperature. And that's because for an ideal gas, you only need one property to fix the state instead of two. So, and that's because you've got that ideal gas law, which adds another relationship between those thermodynamic properties. So let's look at this A22. You've got a column for temperature. So let's say that you've got air at 200 Kelvin. I could pull off the H value, that's 199.97 kilojoules per kilogram. I could pull off the U value, that's 142.56 kilojoules per kilogram. So those are the three columns that you're going to use right now. There are other properties on here that I don't want you to use yet. So this S naught, since that probably doesn't look very familiar, there's probably not too much of a risk of you using those incorrectly. But the PR and the VR values, that's not pressure. It's not specific volume. That PR is also not the reduced pressure, which we talked about when we talked about the generalized compressibility chart. That was a capital R. This is the lowercase r, and this PR and VR, those are what are called the relative pressure and the relative specific volume, and we just haven't got there yet. So I don't want you to use those because we don't know how to use them correctly yet. All right, the other way that we can calculate delta U's and delta H's for a substance in the single phase is if we know the relationship, if we know that CV as a function of T, if we know that function, or CP as a function of T, we can integrate them and we can get an expression for delta U's and delta H's. And that's accurate, but it's also time consuming and difficult, and maybe we want to make things easy on ourselves. And one way we could do that is assume that the specific heats are essentially constant during a given process, meaning that they're not a function of temperature anymore. They don't change as temperature changes. So if we do that, we can develop several relationships. And we're going to skip the derivation right now and just skip right to the chase. So for the first case, this would be if you have a compressed liquid, and these relationships are also applicable if you have a solid. So it's in a single phase, so only in the liquid phase or only in the solid phase. And here they are. Delta U can be approximated as CV delta T, so CV times T2 minus T1, or sometimes you'll see that subscript V dropped, and that's because for an incompressible substance, CV and CP are equal to one another, and so you might just see it written as C. Delta H, also very simple. You've got an additional term though, but it's CP delta T plus the specific volume, which is constant for an incompressible substance, or approximately constant, times delta P. And sometimes, like I said, you'll see that subscript P dropped. Now, we won't spend a lot of time applying these relationships in the compressed or in the incompressible substances. We'll typically use our tables, but I do want you to be aware of them because you may see these relationships pop up in subsequent classes. We'll spend most of our time using these relationships to calculate delta U's and delta H's for ideal gases. And if we make the assumption that we've got an ideal gas, and we talked about how we can use the generalized compressibility chart, for example, to verify that assumption. And if we make the assumption that specific heats are constant. So those are two different assumptions, right? So you might need to verify both of those or justify both of those. That's a better word. So if you make those two assumptions, then you can approximate any delta U's as CV delta T's and any delta H's as CP delta T's. So those are really simple, and those relationships are given to you on your equation sheet, so you don't actually have to memorize those if you don't want to. So now the question becomes, well, we know for an ideal gas, those equations are valid. This delta U is equal to CV delta T, delta H is equal to CP delta T. Those relationships are valid if you've got an ideal gas and you assume constant specific heat. So we've talked about how we justify the assumption that we have an ideal gas. Now, how do we justify the assumption that the specific heats are relatively constant? And there are a couple of different scenarios in which you can do this. Number one, if your change in temperature for a given process is less than several hundred degrees, then your error in making that assumption is pretty small. So let's look at A20, and A20 gives us the specific heats of some common gases. I've just looked at air for simplicity here. And let's look at the line corresponding to 300 Kelvin, because you'll notice that there are different CP and CV values for different temperatures. So at 300 Kelvin, that CP value that you're given, that's the CP that was determined based on increasing the temperature 1 degree of air from 300 Kelvin to 301 Kelvin. So it depends on what temperature you're starting with. And that CV, instead of being a constant pressure process, this one's a constant volume process. You're looking at how much energy it takes to raise 1 kilogram of air from 300 to 301 Kelvin if the volume is constant. And then that last column, K, is just the ratio of those two, CP and CV. And that's just because we have a lot of relationships that deal with the ratio of those two. So we give it a special variable name. All right. So we're going to be using those relationships, delta U equals CV delta T, delta H equals CP delta T, for processes that occur between two states and two different temperatures. Now, if the change in temperature from one state to another is relatively small, say several hundred degrees, then your CP and your CV values are not going to change that much. So if you just look at how CP changes from 250 to 450 Kelvin, that's not that much. But now if you look from 250 to 1,000 Kelvin, that CP starts to change quite a bit. And so if you're on the order of magnitude of 100 or so, yeah, your error in making this assumption is going to be relatively small. But if you're on the order close to 1,000 or more, then 1,000 degrees or more, then the error involved in making the assumption that specific heats are constant and that they don't vary with temperature, your error is going to be quite a bit more. So now the question might be, all right, great. Let's say I've got a process and it's occurring between 300 Kelvin and 500 Kelvin for air. And I've said, okay, well, that's only 200 degrees. So making the assumption that I've got constant specific heats, that's a pretty safe assumption to make. But now what temperature should I evaluate CP and CV at? Because I've got a CP and CV value for 300, I've got one for 400. So what temperature should I actually evaluate it at? And the answer is, if I want to be most accurate, I would evaluate it at the average temperature. So if T1 is 300, T2 is 400, I might evaluate it at 350 Kelvin. Less accurate, but often used, especially in this class, is to just take it at a convenient temperature, and that's 300 Kelvin. That's about room temperature. So typically on a test, I would say, if I was going to tell you to make the assumption of specific heats being constant, I would say, take it at 300 Kelvin. All right, so that's option one. I can make the assumption that I've got constant specific heats if the delta T is less than several hundred degrees Celsius, or just delta T is less than several hundred degrees, period. And I can make the assumption if I've got a monoatomic gas, so helium, neon, argon, and this is reflected in table A21, which I don't believe you have in your tables packet, but it's in the back of your book as well. Don't worry too much about that CP bar, but this is a mathematical relationship that you can use to calculate what the CP value is for various substances on a per mole basis. And you'll see in the box at the very bottom that for monoatomic gases, they are not a function of temperature. They're pretty much constant. And then the last case is if I tell you to. So that's the easiest one. On a test, if I tell you explicitly that you can assume that specific heats are constant, then you can assume them. If I don't tell you that, your safest bet is just not making that assumption and using your tables to look up U values and H values. But if you notice that delta T is relatively small, then you can throw that in your assumptions and you can say, I'm going to assume specific heats are relatively constant because my delta T is on the order of 100 degrees as opposed to, say, 1,000 degrees. So let's work a problem. We've got air. It undergoes a constant pressure process from 300 Kelvin to 500 Kelvin at 1 bar. We want to determine the heat transfer and the work for the process in kilojoules per kilogram, and we're going to assume that the air behaves as an ideal gas. And we want to solve this assuming that the specific heats are constant, and we're going to take them at 300 Kelvin for convenience. And then we're going to take into consideration how the specific heats change with temperature. In other words, we're not going to make the assumption that specific heats are constant. And this process, just by the way, takes place in a piston cylinder. So it's a closed system. It's what we're used to. So here's my give and find and assume. And I'm assuming that air behaves as an ideal gas. It tells me that I can do so. And for part A, I'm going to make an extra assumption that CP and CV are equal to 1.005 and 0.718 kilojoules per kilogram K. And those are values that you take off, that you get from, I think it's A20, table A20, that tabulates specific heats for air and for other gases as well as a function of temperature. So first thing I'm going to do is I'm going to apply my first law. I've got a closed system, and I know that I haven't worked with air yet. I haven't applied my first law to a system involving air yet, but it doesn't matter. It applies to any substance whatsoever. And so here's my first law for a closed system. And then I might want to go ahead and say, probably kinetic and potential energy changes I can ignore. I don't know anything about them anyway. So I get rid of that. And then I notice that, okay, this is a constant pressure process. I'm increasing the temperature from 300 to 500 Kelvin. So I can imagine as I'm increasing the temperature that the air within that piston cylinder is expanding. And so the piston head is moving, and so I've got boundary work, and I've got constant pressure boundary work. And I've got an equation for boundary work, which would require me to assume or to model this as a quasi-equilibrium process. And that would be, if I wanted to get everything in the right units, I'd need to make sure that I have the big W, which is in kilojoules, is equal to M times pressure delta V. So it's the integral of PdV, but the pressure is constant, and so that comes right out of the integral. And then I'm just going to rearrange things, divide through by mass, and get an equation for little q. So that would be one of my governing equations for little q. And then I also, of course, I have an equation for my little w, my work. All right, so there we go. So I'm gonna calculate my work, and my work is P delta V. It doesn't really matter whether I'm assuming specific heats are constant or not. It's the same, it's the same equation that I'm going to use. It's P delta V. So it'll be the same answer for A and B. Now I've got pressure, and then my delta V, this is the change in specific volume. And you remember that specific volume, you do have ideal air tables, but you don't have a specific volume column right there. So what you'll need to do is you'll have to apply the ideal gas law to calculate V2 minus V1. And then what you'll notice is because the pressure is constant, you've got a pressure on the top, you get the same pressure on the bottom, and so those things just cancel on out, and you've got R, the specific gas constant, times delta T. Now remember that specific gas constant, it's calculated, if you don't know it, it is 0.287 kilojoules per kilogram for air, but if you don't know it, in your tables you have R bar, which is the universal gas constant, 8.314 kilojoules per kilomole, and then you need to divide by the molar mass, which is in table A1. So there we go, there's my calculations, and I ended up getting 57.4 kilojoules per kilogram. Makes sense, it's a positive number. I've got an expansion process, and for expansion processes, that leads to a positive number for your work term. It's a work output. All right, so I've got that, check, I've got the work. Now I need to deal with the Q, the heat transfer. So there's my governing equation, and I've got two scenarios that I got to consider. One is if I assume the specific heats are constant, and if I do that, then any delta U's that I have, I've got an ideal gas with constant specific heats, so any delta U's that I have can be approximated as CV delta T's. And now I know my CV is 0.718 kilojoules per kilogram K, and then I just need to plug in everything, and I ended up getting 201 kilojoules per kilogram. So that's the heat transfer that I calculate when I assume specific heats are constant. And now let's see what I would actually calculate for Q if I didn't make that assumption. So I've got the same equation here, delta U plus my work, and my delta U, it's U2 minus U1. And now all I have to do, if I don't make the assumption that specific heats are constant, I can't put that delta U in terms of CV delta T, so I actually have to look up U1 and U2. So I'm going to look it up in my table A22. U1 is evaluated at 300, U2 is evaluated at 500 Kelvin, and I just read off the table and plug in the numbers. And I ended up getting 202.82. So that's really, really close to what I calculated when I made the assumption that specific heats were constant. And it's not surprising that it's close because, well, if you look at the temperature difference, it's 200 Kelvin. It's between 300 and 500. That's a really small temperature difference. And in fact, I probably could have gotten that previous number that I calculated in part A, the 202, I probably could have gotten it closer to this 202.82 if I had calculated based on a CV value taken at, instead of 300 Kelvin, maybe 400 Kelvin. So I would encourage you to maybe try that yourself and see if that gets you a closer number. All right. Well, I hope that was helpful, and thank you for watching.